Welcome to the new session on statistical mechanics. In this new session, we will start with the canonical ensemble. Earlier, we have studied about microcanonical ensemble, and in that microcanonical ensemble, we have the bridging equation S is equal to k log omega, where omega is the number of microstates which depends upon the energy, volume and number of particles. And that bridging equation is S equal to k log omega, where k is the Boltzmann constant and S is the entropy. Using this bridging equation, we will be able to find out the bridging equation is S is equal to k log omega, where omega is a function of energy, volume and number of particles. What we have imagined this is an isolated system. In that isolated system, energy, volume and number of particles. Isolated means there is no exchange of energy or particles, completely isolated. And then we will be finding out omega, the number of microstates possible for the system, and then finding out omega. For example, in the case of an ideal gas, we have omega was equal to, the number of microstates was equal to v raised to n pi raised to 3n by 2 r raised to n whole divided by h raised to 3n into 3n by 2 factorial. And if we encounter the Gibbs paradox, we will have to divide this by once again by n factorial. By using this omega, we will be able to find out the equation of state of an ideal gas. That is, we will be able to find out what is the pressure. From the entropy, if you know what is omega, you can find entropy, and then by using these equations, 1 by T is equal to dou S by dou E, P by T is equal to dou S by dou V, and mu by T equal to minus dou S by dou N, we will be able to find out all the thermodynamics in microcanonical ensemble. Now, we have three types of ensembles. In these three types of ensembles are microcanonical ensemble, canonical ensemble and grand canonical ensemble. In the microcanonical ensemble, your system is completely insulated. There is no exchange of energy and also an exchange of particles. But in the canonical ensemble, the system is a closed one. But there is no insulation is there. Therefore, it can exchange energy with the surroundings, or after exchange of energy or after attaining equilibrium, the temperature will be a constant. Therefore, in the canonical ensemble, we will keep temperature, volume and number of particles constant. But in the grand canonical ensemble, there is a chance that the particles can escape from the system, or particles can be added to the system. And in that case, we will be keeping temperature, volume and chemical potential. All this has been discussed earlier. Now, in this section, we will be dealing with the canonical ensemble. And in this canonical ensemble, the system is in thermal equilibrium, or the system will be exchanging energy with the surroundings or with the environment, and finally, the temperature of the environment and the temperature of the system will be equal, and at that time we will start calculating the thermodynamics of canonical ensemble system. Yes. Therefore, in this canonical ensemble, similar to the microcanonical ensemble, actually what we are doing is we are living in the macro world, and we want to find out the thermodynamic properties like pressure, energy, entropy, chemical potential, etc. And all these things has to be found out from the movement of the particles, movement of photons, movement of molecules, atoms, etc., which are living in the micro world. And from that micro world, we have to find out all the data, and then we have to transfer to the macro world. And in that macro world, we have all these thermodynamic parameters. Therefore, there must be a bridging equation from that connects the micro world with the macro world. And that bridging equation, in the case of microcanonical ensemble, it was S is equal to k log omega. Now in the case of canonical ensemble, we will have to derive a similar equation. For that, we have to take a system in contact with the surroundings. And then actually I will not be deriving those things. You can refer Statistical Physics by Kellen, which is a very famous book. In that book, the whole derivations are given, but I will give you a brief idea about what we are going to do is. That is, we will be considering a system with energy EI, and the energy of the reservoir we can represent by E reservoir. Therefore, the total energy will be equal to E total, and in that we will be representing that by E total, and that means you have a system which can exchange energy with the surroundings, and that system will be having we will be fixing temperature, volume and number of particles of the system. And we will consider the system energy as EI or capital EI, and the reservoir, it is surrounded by a reservoir, and that reservoir we will be considering that as E reservoir. EI is the energy of the system. I will use this as capital E, and EI is the energy of the system. Therefore, the total energy, this is energy of the system plus reservoir, E total will be equal to EI, which is the system energy and the reservoir energy. When the system is exchanging energy with the surroundings, what happens is you will be having a thermal equilibrium. Thermal equilibrium means the temperature of the surroundings and the temperature of the system, they will be equal. Therefore, the total energy, the capital which is represented by E, will not be a constant because it is exchanging energy with the surroundings. Therefore, what will be, what types of energy you can say will be a constant of the system? That energy will be internal energy, which will be representing by U. Internal energy, which will be a function of temperature only. That energy will be remaining constant in the case of our new ensemble, which is the canonical ensemble, and then we will be that we will be considering as a constant. And then you can find out that internal energy, which will be the sum of all the energies. That is, if each state has got energy EI and the number of particles in that state is represented by Ni, then you sum of all those Ni's and EI's and then divide that by N, we will be getting the average energy, because that average energy will be remaining constant, and that average energy you have to take as U, and then this Ni by N. Ni by N is the number of particles in a particular state divided by the total number, which will be always represented as the probability. Therefore, this equation you can rewrite as sum over I Pi epsilon I, and that you can call it as the average energy. That average energy will be represented by, or it will be represented by the letter U. What I am doing is I am following the symbol that is used in Patria. Patria used total energy as capital E, represented the total energy by the letter E and the internal energy by the letter U. Therefore, that notation is followed here. Yes. Therefore, by using, I am not interested in deriving all those things. Therefore, E total I can write that as E reservoir minus plus EI. I can add I can add U and subtract U, which will make the equation same. And then I will find out, I will be using the concept of probability. And by using the concept of probability and rearranging, I can arrive at the equation like this. Pi is equal to e raised to minus ui, ei minus u divided by kt, e raised to minus st divided by kt. And this minus of minus u I can take to the other side. Therefore, my equation will become e raised to minus ei by kt, e raised to u minus ts divided by kt. And what is this u minus ts? U minus ts is a thermodynamic quantity which is represented by A, which is the Helmholtz free energy. Therefore, your equation now becomes Pi is equal to e raised to minus beta ei into e raised to beta A. Therefore, you have Pi is equal to e raised to minus beta ei e raised to beta A, e raised to beta A. This is the probability that system will have energy. Your system is here. At any instant, it is exchanging energy with the surroundings. At a particular instant, I can say the system will be having a particular energy EI. What is the probability that I will have that energy EI for the system at any instant? That is given by this expression. Pi is equal to e raised to minus beta EI into e raised to beta A, where beta is 1 upon kT. 1 upon kT, and A is u minus Ts, u minus Ts. Okay, let us make some mathematical manipulation here. I will take sum over all the available states as sum over I. Therefore, this equation will become sum over I Pi is equal to sum over I e raised to minus beta EI, and this summation is not applicable for e raised to beta E. E raised to beta E. And what is the sum over all the probabilities? It will be equal to 1. It will be equal to 1. Therefore, this is equal to, I can say sum over I e raised to minus beta EI. I will represent that as Q. And then I will have e raised to beta E. E raised to beta E. Therefore, I can take this e raised to beta A to my left hand side. Therefore, my equation now becomes e raised to minus beta A is equal to Q. Now, I take logarithm on both sides. I will get to minus beta A is equal to log Q. Remember, this logarithm is not logarithm to the base 10. It is logarithm to the natural logarithm, that is log to the base E. Sorry. Therefore, beta is 1 upon kT. Therefore, I can rewrite this expression as minus A by kT is equal to log Q, or I can write A is equal to minus kT log Q. This is the bridging equation in canonical ensemble, which is similar to the bridging equation that you have used earlier in our microcanonical ensemble, which was S is equal to S is equal to k log omega. S is equal to k log omega. Now, this equation was in microcanonical ensemble. Now, you have this canonical ensemble. In that canonical ensemble, A is equal to minus kT log Q. In earlier case, we know what is omega, the number of microstates possible for the system. Now, this Q is your quantity in the micro world, which is given by sum over e raised to minus beta EI. What is I? I represents all the states. I represent a state, and sum over I represent sum over all the available states. Or in canonical ensemble or in statistical mechanics, our assumption is that the system will go through all the available states. It will go through all the available states. Therefore, if you want to find the thermodynamic quantities, you have to take all the possible energies, and then you have to sum up this equation. And from this summation, you will be able to get your Helmholtz free energy. This is the technique of canonical ensemble. Yes. Therefore, this is what we have done, and finally, we got this expression A is equal to minus kT log Q. Remember, this Q is a function of temperature, volume, and number of particles. Temperature, volume, and number of particles. And from this A, we have to find the thermodynamics, the whole thermodynamics. But that we will do a little bit later. First of all, let us find out what is this Q. Let us understand what is this Q. This Q is sum over all the available states. Q is equal to, therefore, it is a quantity that we have to evaluate from the micro world. From the micro world. Micro world means the world of electrons, photons, phonons, etc. All these particles in this micro world are inside a metal or inside a star, inside a solid. All this will be continuously moving. And if you want to find out the properties exhibited by all these materials, you will have to take all the possible energy states, and then you have to sum up, and then you will be able to find out what is the partition function. Actually, this partition function is a German word, and it simply means the sum over all the available states, and hence evaluation of the partition function. After evaluating the partition function, you substitute in your expression for A. I can show you that after some time I can show you that you will be able to get all the thermodynamics. Let us have take an example. If your particles are having energy given by epsilon 0 and minus epsilon, only 3 possible energies are there for the particles. In actual cases, it can be hundreds or millions types of energy. But to understand what is your partition function, let me take 3 energies, epsilon 0 and minus epsilon. Therefore, what you have is sum over e raised to minus, sum over I e raised to minus beta ei. Therefore, Q is sum over I means all the available states, sum over I e raised to minus beta ei. Now, your ei is given to be epsilon 0 and minus epsilon. Therefore, your first state is represented by epsilon, second state is represented by energy 0, and the third state is represented by energy minus epsilon. Therefore, your Q will be, what you have to do is, you have to first substitute your first energy, that is e raised to minus beta epsilon, plus you have to substitute your second energy, e raised to minus beta into 0, plus your third energy minus epsilon. This minus and minus will go, you will get a beta epsilon, and e raised to 0 will be equal to 1. Therefore, your partition function will be 1 plus e raised to minus beta epsilon plus e raised to plus beta epsilon. Therefore, this is your partition function. This is how you will be finding out the partition function. This is how you can find the partition function. Yes. Therefore, the 1 plus e raised to minus beta epsilon plus e raised to minus beta epsilon. Now, let us have another possibility. I am giving you energies epsilon, epsilon, 0 and 0, 0 and 0. Therefore, you have same energy is repeated twice here. Therefore, the partition function definitely it will become e raised to minus beta epsilon plus e raised to minus beta epsilon plus e raised to 0 plus e raised to 0, which will be twice e raised to minus beta epsilon plus 2 e raised to 0, which will be 2. Therefore, you can see that energies are multiple energies are possible. Any state, and if you have this multiplicity, what you will be doing is you will be rewriting your expression for sum over I e raised to minus beta ei will be replaced by, in the earlier case you have this 2 here, here 2 is there. Take it to, here 2 represents 2 energies of epsilon, here 2 represents 2 energies having the value 0. Therefore, in order to account for that, I will say that I can say that 2 states are there. Therefore, there are 2 energy states now here, that he will be epsilon and 0, he will be epsilon and 0. Therefore, I can write that as, what I can write this partition function as twice e raised to minus beta epsilon plus twice e raised to 0, e raised to 0, I will write that as 0. Therefore, I have 2 energies are there, which is a function of epsilon. That is this microstate, this epsilon, there are 2 states having the same energy. Here I have 2, which is a function of 0, energy is 0, e raised to 0. This I am rewriting as omega, I can write this as omega epsilon e raised to minus beta epsilon plus omega, which is 0, e raised to 0, e raised to 0. In general, I can rewrite this expression as omega e, and then I can write this as sum over e, omega of e, e raised to minus beta e. And then what I mean this omega of e is how many times that energy is coming, it is repeating. Yes, that is why your Q is sum over E omega of E raised to minus beta E. What we had seen is that in the case of quantum energies, you will be able to see that the same energy value will have hidden degeneracies. Same energies will be, system will be having the same value of energy. For example, if I say that one energy is having value 1 electron volt, because of the degeneracy, quantum degeneracy, same energy, there will be a large number of states or levels with the same energy, and that is called as the degeneracy. Here I had shown that this is the energy of a harmonic oscillator that we will see later on. You can see that your ground state will not be having any degeneracy, but your first state will be having a degeneracy of 3 and your second state will be having a degeneracy of 5. That is, a state will be having, there will be a energy for a state and that will be repeated for that energy will be repeated for a system. Yes. And therefore, sometimes you can, instead of omega of E raised to minus beta E, you can simply write your expression. For example, if each energy level is repeated, you have seen that in the earlier case, you had seen that the degeneracy of the second state, degeneracy of the first state and degeneracy of the 0th state are different. Therefore, in order to account for that, I will rewrite my equation as Q is equal to sum over I Gi raised to minus beta Ei. What I mean is my degeneracies are different. Therefore, I can write G1 for the first case e raised to minus beta E1, then E1 will be having a degeneracy G1, and if my second energy is having a degeneracy G2, I can write as beta E2, and in general I can write this as sum over I Gi e raised to minus beta Ei. Therefore, this is the new form of partition function, new expression for the partition function. Okay. Now, coming back to your degeneracy, you can see this degeneracy for a quantum system, it is the expression you will be deriving in your quantum mechanics. When you are solving the Schrodinger equation, you will be naturally getting what is the degeneracy. How many degeneracies are there for each state, you can find out. For example, in the case of a harmonic oscillator is a quantum system, and its classical energy was p square by 2m plus half k q square. If that Hamiltonian is operated on a wave function, then you will be getting energy eigenvalues and the wave function, and those energy eigenvalues will be representing as it will be represented by, for example, the energy eigenvalues. You can say En will be equal to n plus half. This is the quantum energy for a one-dimensional harmonic oscillator. If it is one-dimensional, this is the expression for the energy, and if it is two-dimension, you have the 0 point energy will be coming twice. Therefore, this will be n plus 1 h cut omega, and in 3 dimension your 0 point energy will be coming twice. Therefore, in n plus 3 by 2 h cut omega, and then each level, this n is from 0 to infinity, each level will be degenerated. And in the quantum harmonic oscillator, for the first one dimension, the degeneracy is 1. One dimension, it is degeneracy is 1. In the second, in the 2 dimension, the degeneracy value will be equal to n plus 1, and in the 3 dimension, it will be equal to n plus 1 into n plus 2 divided by 2. Therefore, we will find out what will be the degeneracy equation is given by in 3D. In 3D, it is given by n plus 1 into n plus 2 divided by 2. Therefore, when n is equal to 0, that is the ground state. This is the diagram that you had seen earlier. This is the ground state, n equal to 0. n equal to 0, if I substitute here, this is 1 and this is 2. 1 into 2 is 2. 2 divided by 2 is equal to 1. Therefore, there is no degeneracy, only single state is there. Only one single state is there, therefore, there is no degeneracy for the ground state. If I put n equal to 1, therefore, I have the second energy level n equal to 1. If I put n equal to 1, this will be 2, this will be 2 and this will be 3. This will be 3 whole divided by 2. I will get this as 3. Therefore, instead of this 1, what I will be having is this one level will be, there will be 3 states the having the same energy. I will have the same energy with the 3 states. And then for n equal to 2, if I count, if I take n equal to 2, I have this is equal to, degeneracy will be equal to, that is 2, that is 3 plus 3 into 4 divided by 2. 3 into 4 divided by 2. This is 2 plus 1, 3, 3 plus 4 divided by 2, that this will be 6 times degenerated. 6 times degenerated. Therefore, this is how you will be able to have this equation, that is this is what we mean by this expression n plus 1 into n plus 2 divided by 2. Therefore, using this you will be able to get the partition function. The partition function, earlier I had shown you, the partition function is given by q is equal to sum over I gi e raised to minus beta ei, and then you can use this gn value there and then substitute that expression here. You will be getting q is equal to gn e raised to minus beta en. This is how you can evaluate the partition function for quantum systems. Okay, I hope all these things, the basic ideas of partition function, you can now I had given to you, and we will stop this session. I hope you enjoyed this session. We will come to the details of partition function in the next session. Thank you.